Yeah, we
Yep,
should have
and it
started
did.
recording.
It
Yep.
does. It says started
Perfect.
by, yep,
Good.
recording and transcription have started, so that's good.
All righty.
Alright.
Sounds good. All right. So let's just start off with the slide show, and then we can go from there. So
Okay.
yeah,
So,
we start with the slide, and then I've got the formula down. So
should we introduce
oh yeah.
ourselves?
Okay. So yeah, we can put video down for now. Right there. Perfect.
Okay.
All right.
My name is Gabe Batuk. I am the chief engineer of Comet Rocketry.
And my name is Logan Murray. I am the director of Comet Rocketry, and we are here to do the safety review today.
Yep.
So starting off real quick, I'll just go to the slide. You can take it away. Our rocket is called Sledge. It is a 10K COPS rocket. It has an M1850 motor, single, and it is single split, and it is a non-deployed parachute.
A payload.
Yeah, payload. So, sorry.
Yeah, so single split. Single split means it only has one opening for a main and a drogue. We use a
Okay.
setter TD2 to hold it down, to hold the main down while the drogue is deployed. And we'll sort of show through our presentation how we've actually tested that before, and we are fairly confident that that system works really well, and that we have sort of most of the pitfalls of the system worked out. So, yeah. Any questions so far?
Nope, so far so good.
All right.
Alrighty. We'll go on to, so we'll start out by going through the electronics test rocket that we have built and tested throughout the semester. We'll go into structures, show you our motor, show you our payload, show our recovery systems from the avionics and mechanics standpoint, and also our factors of safety. So what I'd like you to do, Gabe, is actually pull up our video onto that so it's in the recording as well.
Yep. So this is
Oh.
our.
Yep, perfect.
So we're about to show this rocket. Someone we know took this video. I'm not sure who. Yeah, thank you again for the video.
Yeah.
So yeah, just for reference, this is the flight. This was the first flight, which happened back in February. So we had our rocket successfully fly on a K480 up to an apogee of about 5,800 feet, and successfully deploy and land safely. We also reflew it a couple weeks ago for the first time on a K1275, which was an even more successful flight in that we didn't have the main parachute only half deploy. We had the main parachute fully deploy. And yeah, it was a great flight to see. And
Yep.
Yeah, so.
Yep, and then I want to put the video on there because that's where it's going to be recording. So we need all of our stuff that we're showing.
Recording, yeah.
Yeah, no, I'm saying like our phone video on there.
Oh, no, it is recording already. It's recording the whole meeting.
Oh, it's recording the whole meeting?
Yeah.
Okay, perfect.
Right.
All right.
Yeah.
Yeah.
So our video is going to show up on the recording, just clarifying that.
So
Yep.
So yeah, here's the rocket. It's a little stripped down right now because we just flew it. And there are some parts of this rocket that are used for other parts of we use for our Spaceport rocket, like the TD2 and some of the electronics. But starting from the nose cone down, we actually, this rocket is a pathfinder for basically every part of our Spaceport rocket. So the nose cone is actually a custom made nose cone. That's a 3D printed element with a fiberglass laid up over it. And so it's a solid piece, and that actually allows us to create custom nose cone geometries. So for example, on this one, it's a hack series with out of fiberglass, and it has like this body tube geometry is a non-standard geometry. Like it's not a standard, easy to find geometry like that you would find on an off-the-shelf nose cone. So that allows us to sort of build more custom profile for the rocket. The body tube is fiberglass, and it's actually, we did the layup ourselves on a aluminum mandrel. The fins are Waterjet G10 with just epoxy fillets in there. And yeah, on the inside, we have some of the bulkheads, but not everything is in there right now. We'll actually show them later on in the presentation. So.
Yep. So just to clarify, obviously not our Spaceport rocket, but this is what we've been doing a lot of the tests on our airframe, our composite layup methods, our recovery systems, our electronic systems, all that's being tested through here. Yeah. And so we can go into the more Spaceport side of things now. Starting off with the,
It's not done yet, as you can see. We're still missing, well, for example, this tube we have like still on here because it is easier to work with, but we're going to cut it. And then we have our fins, which are only partially tacked in right now, and we're going to finish. Well, we've been working on really with alignment. We've been trying to be very, very cautious about making sure these are perfectly aligned, and had some issues with that lately, but we think we figured it out, and hopefully we should get these fully in by end of day tomorrow. And then yeah, going down, we have our coupler, which is an 18-inch coupler that sits in the middle here. And this connects the two sections. Then we also have our all the way up to our nose cone, which is a 36-inch, 24-inch nose cone, 3D printed with a fiberglass layup on top of it. That allows us to, again, create a custom nose cone geometry. We also have on the inside aluminum bulkheads. So this is an example. This is a piece of the thrust recovery of the recovery structure in the thrust section. So it's two aluminum bulkheads which are bolted to the airframe. They use 7 series aluminum, which is a little bit stronger, but a little bit heavier than 6 series aluminum. So this is 70-75 as opposed to 60-61. And we think that added strength just helps us a lot with confidence. And then each bulkhead is bolted in with 8 M4 screws, which allows us to have a really high factor of safety on the bulkheads, which we'll show later in the presentation.
Yep, I'm gonna go pull up the slide real quick on that.
Sorry, we're going kind of fast. Do you have any
Yeah.
questions?
So
No, you guys are good because any questions, I'm keeping notes, and then when you guys are done with that, any questions that I've started on my notes, we'll go back and I'll have you guys show me in a little bit more detail. So
All right.
you guys, so far you're doing a great job.
All right, thank you. But yeah, so this is sort of just the airframe that we have right now. We're largely done with it. There's a few things that we want to do to there's some finishing that really needs to happen. But for example, for the test flight that we're planning on making, we're not going to paint it because, I mean, if it fails with a paint job. But we will have concepts for a paint job as well.
Mhm.
But we're fairly confident this rocket will have no problems when we fly it. Over here, we have all of our motor stuff. We brought one of our motors in.
So yeah, over here, we're gonna go on to motors real quick.
Yeah.
I will, yeah, there's a proportion stuff. All right.
So we have our just to show that we have everything for our motors, we have our casing and an M1850 here. We have 2 more to spare, just in case we need them. And so we just have everything that we need. There's no cross loading or anything fancy happening here. Over here, we have our payload. This is just one of the payload ground stations. These still need a little bit of finishing, but essentially our payload experiment is trying to track the rocket. And so what we're going to do is we have these. So this is the aluminum chassis for the rocket, for the payload. But we have a lot of these PCBs on board the payload that are, so one of them is an IMU PCB, and one of them is a radio PCB. And these are going to help sort of track our rocket as we fly, and that's our primary experiment. These ground stations, we're going to have 4 of them scattered throughout the recovery zone. And the whole idea behind them is that they just sort of are listening for chirps from the rocket, and we'll take that data, and we're going to try to basically triangulate our rocket as accurately as possible. We also have, just in case, a payload, a boiler mass payload that is sort of a mass simulant instead of just going with this full payload assembly in case we don't have it really ready. And the main reason for that is just to sort of, even if we don't have our payload ready, the rocket won't be ready to fly. So, I mean, our rocket will still need a payload to fly safely. So that's our sort of backup there.
All right, moving on to the next thing. I'm just going to update the slide real quick. We're going on to recovery. We'll have the flight profile. We'll talk about that later. But starting out with recovery, this is the electronics side of recovery.
So this is our electronics bay for our Spaceport rocket. It follows a very similar profile to the recovery structure on the aft section of the rocket, just with the avionics bay on the inside. In here is actually just a fit test section of it. The avionics bay is designed, but we're missing some of the parts aren't in yet. Those are just 3D printed parts that we're really missing right now, so it doesn't show everything. But these parts don't actually carry really any load. There is these all-thread pieces that connect all the way through both bulkheads, which allow obviously the force of the recovery structure to be dissipated across the entire system. We also have one of our custom developed SRAD flight computers. These are ride-along payloads. So these are one of the things we've been working on trying to develop our own recovery system. And that's sort of how we get around. And yeah, so this will be riding along. We also have over here sort of an example. This was what was flying on ETR. So we have one of the, this is one of the other recovery, SRAD recovery systems. We also have a featherweight, a Blue Raven on board, sorry, and a featherweight tracker. And both of those are going to be on our Spaceport rocket as well. And we also have an additional AIM extra on board. Also showing off sort of, this is what the recovery structure on our Spaceport rocket is going to look like. We have a tender descender TD2. So you can see here, it's a very similar structure with just a tender descender TD2 attached here. And that's on an eye bolt. Although the eye bolt's going to be bigger on this one because we've noticed that there's a lot of force that acts on the tender descender. So we're trying to basically up the level of force rating that it has. So it's a little bit, it will have a little bit of a safer flight. And then, yeah, similar eye bolts, we should be fine there. Moving on to our recovery, like structural elements. We have here all of our parachutes, linkages, and our shock cord. So we have a 10-foot Fruity Shoots parachute and a 3-foot Fruity Shoots drogue as our drogue parachute. We have a deployment bag, which is what the primary parachute, our main parachute will be sitting in. And we have our 5/8 Dyneema shock cord. This is overkill, but in all honesty, we really want the factor of safety to be really high on almost everything. We're really just trying to make sure that we don't have any real issues with, like, we're not going for performance. We're going for a rocket that'll fly safely. You can also see that too with our soft shackles, which are massive and way above the load rating of other elements of the system. So, yeah.
All right. And so kind of just to wrap up the overview, let me check. If you look at the slideshow, we'll go back to that real quick. I'll turn off my camera. We'll just start kind of like at some of the more detail-oriented parts of the rocket. So when it comes down to the simulation and airframe, first of all, you'll notice that, again, we're flying on a 6-inch diameter and we're at 110 inches in length. When it comes to the actual liftoff weight, we're at 54.2 pounds. And then, yeah, we have a good stability. I think the stability was what, around like 2?
It's never more than like one. It's never less than 154.
Yeah, it's never less than 154.
1.54, sorry.
Yeah, propulsion type, classic M motor. There's not really much more we can say here. We've run all the simulations. We can go into kind of that. So on the flight profile, this is the more important part. So we have around an 8-to-1 thrust to weight ratio. We have the minimum static margin right there is a 1.5. So it never gets lower than that. We're going to target around 10,000 feet, but we predict it's going to be more around 9,200 feet just based on our rocket pie sims. The max G's it's going to pull is around 9, and then it's going to depart off the rail at around 93.4 feet per second. And then velocity at deployment of our main parachute is 123. Again, we want our drogue, we want it going down fast, but not too fast. So that was the feet per second that we thought would be most optimal. And then when it comes to recovery, I think we already talked quite a bit about this, but the main is going to deploy at 1,500 feet. Our shock cord is 3/16, which is way overkill. And our cord length will, be cut to 60.
It's 5/16. That's an.
Oh, 5/16. Oh, yeah, 5/16. My bad. Ugh. And then, our drogue descent rate's around, 16 feet per second. And we're using a TD2, so single deployment.
Wait. Okay, hang on here, because your drogue descent rate, that I assume that you really mean your main descent rate, because 16 feet per second.
Sorry, yeah. So, on our main parachute is when it's fully deployed, it's 16 feet per second.
Oh.
Yeah, we swapped those.
That is another
Sorry.
typo. Whoops, sorry, that's a typo.
So the DTAG, I think the 126 feet per second might be faster than what the DTAG allows.
I believe in the DTAG, it's 150 feet per second.
Okay.
Yeah.
Yeah, I definitely double check that.
Yeah, I checked that before, and I believe it was 150 feet, but again, I could be wrong. So.
Okay. But just double check that.
Yeah, absolutely.
How big is the drogue?
The drogue is a 2-foot drogue.
Okay. Yeah, just make sure that if it's depending on what design drogue it is at Fruity Shoots, make sure that you're prepared to fully answer the descent rate. And 150, I know that it's changed, and I saw it, but that's most of the folks. Most of the views that I've done have been under 100 foot per second.
Okay.
So and fast is not terrible, but especially since you guys are doing a tender descender, I think you'll be okay. But just you might just in case have maybe a backup larger drogue chute if that's possible, or just verify that 125 feet per second. You might get a little bit of pushback on that. That's
okay.
I do small rockets. A lot of my 38 millimeter and 54s, I'll let come down without a drogue, and they'll come down because they're going to 25,000 feet, like my little 54, and it takes forever to come down. And so, but it's a 3-pound rocket, right?
Right.
Yeah.
Okay.
So just give that a little bit more. Double check the DTAG, and maybe be prepared with a larger chute that in case it gets pushback. Yeah.
Yeah, absolutely. There's nothing that'll hurt us from getting a larger chute. So that's definitely, I'll put that down sort of on our notes. Things to get.
Now, is Ken your who's your mentor?
Oh, sorry. Yeah. So our mentor and flyer of record is Ken Overton. So.
Okay. Yeah, you just might verify with him what what he says on that as well. So.
Yeah, he'll absolutely know what we should do there. So,
yeah.
And yeah, I guess I could speak on Ken a little bit too. He comes around a lot, has helped us out a lot with sort of a lot of our design choices, a lot of our methodology behind how we were building it. But I mean, he does not like directly telling us what to do, but making sure that we're staying within the rules of the competition and trying to stay reasonable with how we're doing things and why we're doing them. So
and I know that this is recorded but it is what it is. But one of the problems that we run into is when you get to the convention center, the safety reviewer is kind of just arbitrarily assigned. It might not be me, it might not be Ken, it's just whoever. And everyone has different ideas, and we don't have super hard and fast rules. And so as a reviewer, I might be, 125 feet per second is fine, but you might have a different reviewer that says, oh no, it shouldn't be over 100 feet per second. And so you kind of want to be prepared for some of the just variation in what an individual reviewer might find to be acceptable or not acceptable. And so if you just keep that in mind about that descent rate. So
all right, yeah, absolutely. I mean, it's just another drogue pair. We absolutely can pack another drogue parachute. That's a little bigger. So
wanted to bring up the attention on the screen. Just talking about kind of recovery factor of safety. So we've run some calculations. Just to kind of verify that some stress points on our rocket aren't going to be failure points. They're kind of labeled right there, A, B, and C. And we're well above a factor of safety of 2.5 on all of these. And when it comes to shear and tear out, way above factor of safety. So we're more just concerned about kind of point A and the tensile stress that's going to be happening during ejection. So that's going to be our kind of primary point of reinforcement. But as of right now, our calculations are showing it's fine, and we're just going to make sure we beef that up right before competition and during the assembly of our rocket. Hot rocket, yeah.
And
so
that's
quick.
Sorry.
Well, just a quick question on part A there. Those bolts look like they were 3/8 all thread, or were they 1/4 inch?
They are 3/8 all thread.
Yeah. Okay. See, I've had a fair number of teams using 1/4 inch, and man, 3/8 makes me a lot. It's obviously a lot heavier, but the increase in strength is considerable over a 1/4 inch, and so I think that's a good. So that's good.
One of the things we're looking at too, which we haven't fully decided on yet, but we have both of them, so they're both options. Is we have both steel and aluminum. We want to do a little bit more calculations and see a little bit more about using aluminum, but that pretty much negates the weight issue. And those would be 6061 aluminum all thread bolts, or just steel all thread section. It really depends on sort of how confident we are in the strength of the system. whichever one we'll use in the end. So, but those are just drop-in replacements. They're both the same length.
Okay.
No issue.
And they're both, yeah.
Replacing both. So, yeah.
And they're both 3/8. The aluminum is also 3/8.
Yeah, they're both the exact same bolts.
Okay.
We have no issues between the two. We also have some sort of designs to show off the paint because we don't have any paint jobs right now. We're still kind of deciding on which ones to do. And these don't have the numbers displayed on them, numbers or sponsors on them yet, but both of those will be on there when we have the rocket done.
So, and I will point out that white is good because it does get very hot, and
oh,
too many people use dark colors, which of course, you get the radiant, you get the thermal load from the black paint or whatever. So
one of the things we're going to try to do with paint is we actually have a paint additive that ups the reflectivity a lot. And this will hopefully, the entire rocket's going to get painted in this. And what it does is it'll help really deal with shedding heat from the flight. So, yeah, just got to show it off because it's cool. And
interesting. Yeah. So the the Blue Raven it'll give you the internal temperature. And it would be interesting to maybe do a side by side with your existing rocket. Put the Blue Raven in that, let it sit in the sun for an hour, and then try it in that and see if there is in fact a difference. And you don't have to do that obviously at the spaceport, but just sometime between there, because that's a really interesting additive. I hadn't seen that before, and so that's something that might solve some issues for folks.
Just one more look at it if you want to.
Yeah, if you want to, get it for yourself.
Thermal cells, very interesting. Yeah.
So just sort of to show that we've been thinking about heat and temperatures and trying to make sure that like our rocket doesn't melt on accident while we're out there.
Yeah.
Obviously, spot for carbon tip, which we're still getting. It's machining right now, so we're waiting for that to get in.
This is an aluminum carbon tip.
Okay.
The rocket doesn't really go fast enough to need a carbon tip per se, but it's good to have the leading edge, I guess, of the entire rocket to not worry about deforming. So,
yeah.
All right, go back to slide.
Yeah. That's pretty much it for our slides, I think.
Okay. Well, and you guys already mentioned this, but make sure obviously that you have the numbers and you need the numbers on both parts, right? You need, since you only are breaking into two pieces, and the nose cone stays attached, right? So it's I assume it's going to break where that horizontal line is thereabouts.
Yeah. So we can show over here. Okay, fine.
Yeah, go for it.
Sorry.
Quick on flip camera.
Yeah. So over here is where we have the rocket splitting into two. Let me get that out of the way.
Okay.
And so there's this is a little bit sketchy to move, but
here.
Yeah. So you can sort of see
that's good. Yep.
in there. We don't have because the top of the recovery hardware is this section. And you can see actually on here we have the aluminum all thread bolts just because we've been just using it. But this slides in there and will be bolted in on the side. And that holds the entire sort of recovery section. So
what kind of weight savings? I don't know if it matters, but I will tell you that the faster your rocket goes, the less likely it'll have trouble. A little bit less the better stability you can get off the rail, the better. And of course, do that with a bigger motor or a lighter rocket. And since you've already got the motor, I don't know what kind of difference in weight the aluminum all thread would make versus the steel. I use aluminum in all my what I call my go fast rockets, my little Mach 2 Plus rockets, and I use all aluminum components in that, and it does make a difference. The steel is obviously very heavy, and as long as you still have the safety margin, you guys are kind of on the edge in terms of getting to that 100 foot per second kind of cutoff. And so if you gained even a couple 3 feet per second, that might be it'd just be interesting to do the sims and to see what the difference in weight makes for you.
One of the other things we've noticed too is that this also helps. We're a little bit marginal with stability. With a 1.5, I believe the minimum stability on stability on a set is 1.55 or 1.5, and our minimum stability is measured at 1.55. And we're kind of worried about this lower section being a little heavier than we've predicted. So this is also kind of helps with that, with sort of shifting some of the weight forward if we use these aluminum all threads and some of the steel all threads at the top there. So that just sort of takes us from more borderline to a little bit safer. So
yeah, that's good. Yeah.
Part of the other reason we were planning on using these is because it lets us sort of shift around the weight a little bit more. So, yeah.
Okay. So you guys you're done with your presentation. So now or with the slideshow, is that correct?
Yeah, just gonna make sure we didn't miss anything on that real quick though.
Yeah, we could go over.
Yeah, we're just gonna run through. It's not extremely comprehensive, but if you have any questions about any of this,
Yeah, you can see there's our CAD that shows sort of our payload. Payload just is bolted in through the airframe. So there's like a coupler it's sort of sits on that's attached to the top of the eBay, and that gets bolted through the airframe. Can you back a slide?
Yeah.
And that will just get bolted basically through the airframe. It's attached to the airframe. It never needs to move during flight. There's also, and this piece isn't here right now, but there's also a plate at the top here. Our nose cone, if you can see, it says nose and radio bay. We have 2 radios on board the rocket. We have an AIM extra and a featherweight tracker. And because we have a carbon fiber rocket, those signals can't get out of the rocket normally. So we basically created this big sort of window in our rocket in our nose cone. And so these, that's where our radio sits. It's also for the payload radio, which also extends through there. And that'll sort of let us, it should help with, dealing with we don't have to cut any special holes or anything in our rocket to deal with the radio. Yeah.
Okay, so so let's talk about the nose cone. If you want to go back to the camera for a second, and
perfect. Yep.
So I assume the length of the shoulder is at least a half a caliber, and it doesn't actually really matter since it's not being ejected. I assume it's mechanically attached.
Yeah, it is it's over half a caliber. Sorry, it's a little bit of a pain to pull out, but
okay.
We actually have a full caliber, and it's fully attached through.
Okay.
You can kind of see it's a little messy down here. We need to clean it up, but you can sort of see how thick the fiberglass is over here. We also have,
okay.
Yeah, so you can kind of see like the fiberglass is still the main structural element. This was 3D printed on a polycarbonate to deal with, also to make sure that it doesn't fully deform in the heat. But yeah, this is.
And so, when you said you made it, you created an opening for radio. You're just really what you mean is that's not radio opaque, or
it's fiberglass, so it's not radio opaque.
Just regular. Okay, so it's not okay.
So it's just,
at first I was concerned that you'd cut a hole, and some people actually will cut waveguides into the carbon fiber structures, but you don't need it if that's just regular fiberglass.
Yeah. So this is the whole system's designed to be radio opaque and be in sort of the most open part of the rocket. So the radios, this is a really cavernous bay. It's, I think in total only about a 1/4 inch thick. So we can mount our radios really high in there too to give them a better sort of look down capability over the shoulder. So yeah, that just slides back on them there. We can also show sort of on our coupler. This is, see, it's kind of hard to get in, but we never want it to come out. So during flight. Something actually to point out in our coupler too. Our coupler is 18 inches long. It's 2 9-inch sections. And that's actually a sort of an artifact from the old part of the DTAG where it said couplers had to extend a caliber and a half into the rocket. And so this is just that sort of showing the.
Is there what's in the coupler?
Is
there anything?
No, there's nothing in there. There's actually the coupler just sits in the. Will sit sort of in. This is what we call the recovery bay or parachute bay, and so it'll sit sort of right here. This can go in. Right.
Be very careful if you do that.
It's a little bit of a pain because this part is not supposed to slide off. So it'll be attached to the lower section here.
Okay.
And so this slides in 9 inches and then slides in 9 inches on the other side. So it's over a caliber and a half of length on both sides, which gives some advantage to
Right. So is the nose cone going to be? I'm sorry, is the parachute going to be contained in that, or what during flight, what will physically be located inside that coupler?
Yeah, so both the drogue parachute and the main parachute, so I can sort of show on here real quick. It's really hard to see here because it's not quite visible right now, but it is sort of marked out. You want to come here real quick? Right here, we can see the marks where the bulkheads are going to be.
Okay.
Just keep your
They're sort
hand there.
of like really,
Keep your.
yeah. I don't want this to fall. Sorry. So these are sort of sorry, not the coupler. I'm sorry. This is where the bulkheads for the eBay are going to sit for our electronics.
Okay.
And so over here is really where the main parachute's going to sit when it's held down by the TD2, and then the drogue will sit back here, sort of. So when this kicks
Okay.
out, the drogue will just sort of flutter out, and then we'll keep the TD2 held. The TD2 will hold the main parachute in until we want to deploy it. So yeah.
Okay.
So both of those sit in that section.
All right.
We're using black powder charges, the latex style ones where you put them into a latex tube. We have a 5 gram and a 7 gram black powder charge, but we need to check some of the math on that real quick too, to make sure that those are the exact numbers we want to do. And we still need to do charge testing on this system, which we're hoping to be able to do soon once we have the bulkheads in and all the mass
Yep.
in place.
I mean, we're doing the fins right now, so should be
Yeah.
very soon.
Okay. So, and the 2 test flights that you guys have had, you've used the tender descender. Is that correct?
Correct.
Okay, that's good. And that's
We can.
that's good experience, because the tender descender, while works really well, it does require some correct rigging, and it's a bit of a challenge to rig the first time. So
it's worth pointing out, we actually had an issue with our first flight a little bit. We had our main parachute only half deploy. So one of the things we did to sort of rectify that, well, one, we just looked back at our lengths and re-rigged the entire system to ensure that we covered all the lengths properly. We went in and checked our flight computer settings, because one of the things that we looked at that could have possibly caused an issue with that flight was an issue with our Blue Raven flight computer. We think a firmware update might have messed with some of the settings, which is a little thing to check while we're at the competition. And then also we noticed too that because our parachute half deployed, one of the things that we did is we actually oversized our parachute for a spaceport rocket. So a 10-foot parachute's a little overkill for a rocket that only weighs about 36 pounds when it's fully spent. And so to deal with that, we have basically a parachute that even if it half deploys like it did with our first tender descender flight, which we fixed in our second flight too, we'll still hopefully be, we'll still have a safe landing because we still have plenty of sort of parachute to deal with. So.
okay.
Yeah.
As part of your checklist procedure, I would definitely recommend having a tender descender packing check part of the checklist that's very specific to how the checklist or how that should go, because that will probably, and when you guys are at the Spaceport Cup, you have to have printed copies of your checklist, and there's kind of three parts of that checklist. One will be arming the rocket for, when you're getting it ready to fly it.
Right.
The second part, you'll need a de-arming or safing procedure if it's on the pad, and let's say the weather scrubs the launch and you got to go take it down. So you need a safing checklist for it on the pad, and a safing checklist for if it lands and the charges haven't gone off, and just a recovery checklist like, hey, what do you do when you go get the rocket?
Yeah.
So make sure that you bring printed copies of those to the convention center for the safety review.
Yeah, we have a safing procedure for we have a safing checklist for like when it lands, and we have a pre-launch checklist, but it's good we'll need to work on a safing checklist for at the launch too. So
yes, and actually that happens more than people would like it to happen. But if the weather comes up and you can't launch, if I'm out there and you don't have a printed safing checklist, I'll get pretty cranky. So
okay, we'll make sure that you keep that just for you.
Consider it done.
Okay.
But yeah.
Consider it done.
That's good.
But yeah.
All right. Hang on. Let me keep going. So yeah, make sure that you get your team number, and it says frequency. If you have anything that uses a, and it's actually a good idea to, even if you just use blue tape. I don't know what the detail says about the actual frequency, but a lot of times people don't really know what frequency their Blue Raven, not the Blue Raven, sorry, but the featherweight tracker is on, and that's a good idea to keep track of what channel it is. Like, is it 22B or whatever?
Okay.
Yeah. So make sure you note that somewhere.
Oh yeah.
Yeah, we're actually gonna write this stuff down on the whiteboard.
Yeah.
I'm just signaling to Gay to do that. So we'll,
Yeah.
well, actually, this is perfect because we can make a little checklist and complete that really fast.
Yeah. And that's And and it says DTAG 8.7 and appendix F on the DTAG for rocket marking and tests for making sure that you have all that stuff on there. Let's see. Couplers look good. Stuckler sound. The number 4. Tell me again about, you said some M4 screws.
Yeah.
Are you screwing through the wall of the body tube to hold the coupler in? I'm not exactly sure where the M4 screws come into place.
Yeah, so they bolt through the body of the rocket.
So-
We did that on our last rocket. So you can see sort of over here, the bolt holes here.
Okay.
And then you can sort of see also on this rocket here how we did that as well. Although this is, if you want to show over here.
Yeah, sure.
Okay, we did this. We have experience doing this before. We did it on this rocket. Some of these holes are a little bit messed
So
up
let's-
because of some work that we ended up having to do. But yeah, so
Okay.
and that.
So how many do you have of those going around your rocket?
So we will have a total of on the outside. I think we'll have a total of 32. My bad.
So sorry, on how many it looked like you had 4 holes drilled in each one of those bulkheads that penetrate from the rocket into the bulkhead?
There's 8 holes drilled on each bulkhead, and because there are 2 bulkheads on each side, it gives you a total of what's the word? 32. Well, I can't do math right now.
Man, you might need some caffeine, man.
Okay, got it. I just want to make sure that because obviously, especially on the bottom rocket, the bottom part of the rocket that has the motor case, when it hits the end of that shock cord, there's going to be a lot of kind of shear stresses on those screws, and if you have 8 of them, that's good. If there was just 4, I think I'd be concerned, but 8, I think you're in business.
Oh, with the all thread, what that actually lets us do too. So we have some extra redundancy in here as well in the system. So if I can show here, we have because the all thread, these are coupling nuts that can couple the all thread to the actual eye bolts. So even if this bulkhead were to blow, we have an entire other bulkhead over here that will also be able to take the force.
Okay.
So the actual total system is 16 bolts. So yeah.
And that's nice. I like that. That's a good setup. Yeah.
And we did the math too, and this actually works fine with just 4 bolts, but we ended up bumping it up to 18. We bumped it up. To 8, just to make sure we're safe.
So the weak point isn't going to be the nuts so much. It'll be the shear strength of the body tube, because you've got carbon fiber that has to resist those nuts pulling against it, right? And it's the carbon fiber that will be kind of the weak point in terms of so having it spread out over 8 bolts. I think you guys are in good shape. So
We gotta take that.
Kind of show.
Hold on one
It's a little
second.
pain. We'll take the coupler out to sort of show. Just to sort of show, we have 3 layers of.
We're back.
So we have to actually hone this section of tube here to actually get this coupler to fit. But we have 3 layers of carbon fiber in there too. So this is an eighth of an inch of carbon fiber in total for the. This is 3 layers of 20K 2x2 12 carbon fiber, and so we believe that this is strong.
yeah.
That's like the best way to put it. Honestly, it's going to be incredibly strong. So the rocket is sort of really supposed to be just very overbuilt. That's the way we just make it tough, and so hopefully there won't be any issues with flight because of that. So.
All right. Let me just hang on. Let me just look at my list. So far, we've done nose cone, body tube, coupler. I'm pretty comfortable with recovery. The fact that you guys have flown 2 flights with the tender descender, that's great. That's a good thing. And again, just make sure that I know that one of the things that almost all reviewers are going to do are going to grill you pretty hard on the way your recovery is set up, and so make sure that you have a good, and especially if you have, you can talk through how it's going to be connected, and they may even do what I call the walk test, where they'll make you pull it and walk it out, and so they kind of see how everything is going to be, played out when you're at altitude.
We actually do that. We do that already with when we rig our systems. The first time we actually rig it, typically what we'll do is we sort of have the lengths pre-planned, and then we sort of walk it just to see how we see the system. So one of the things we actually caught on, for example, with our test rocket was when we walked the lengths, while the tender descender deployed, we noticed the lower section of the upper section of the rocket would start to drop further and further. And we were concerned because what was happening was as the tender descender was deploying the main parachute, we had the chance of the main parachute and the front section of the rocket and the aft section of the rocket basically passing each other. And so that's a really big concern. And we wouldn't have caught that without actually walking the whole system. So yeah, that's pretty much standard for us now. Just trying to walk the whole thing. So
yeah. Actually, I had video that I shot of the main inflating, and the fin can was up here because the way the drogue was rigged. So the fin can was up here, the main inflated, and then the fin can hit the top of the main, and it wrapped perfectly around it, and nothing good happened after that.
Yeah.
So you generally want to try to keep the fin can below, right, so that when the main inflates, the fin can can't drop into it, or enough space between them that that's not an issue. So anything that can happen will happen eventually. That's kind of what I've come to believe. So
so we've been trying to stay vigilant of making sure that we catch something like that earlier than just letting it sit. So yeah.
Good. Okay, a couple other things, and actually we're in pretty good shape. I will tell you that the bolts in the payload, I understand your desire for mass, but those loose bolts in the payload, I got to believe that a lot of safety reviewers will say no.
Okay.
And so now, obviously, there are teams that put just 8 pounds of lead in their rocket, but I think it's the loose bolts that might be a concern.
Yeah. So that's our dummy payload mass. That's just for testing.
Okay.
If we end up doing an actual payload mass, we'll probably use something like sand, because lead is actually banned in the DSEG. So we can't use 8 pounds of lead. But actually, it's worth putting out with those bolts too. They're not actually loose. They're potted bolts. So there's actually epoxy poured up to the top of the bolts in there. So they're not actually.
Perfect.
Yeah.
Okay, and that would work if they're potted. That's fine.
Yeah.
But, or if you had them screwed in or just retained somehow. But okay, good. I just want to make sure that.
Yeah, we were like, oh, do we want to fly a big piece of shrapnel into the air?
Yeah. Okay, I didn't want to use the shrapnel, but that's kind of what it would have. I'm sure most safety reviewers would have said that.
Yeah. So that's so we potted it a long time ago to make sure that we don't even miss it. Okay.
And those plastic spacers in the AV bay, I was a little concerned about them. They're kind of golden ones that you had, and they were kind of like whatever hourglass shape. But they're not gonna ever really be under any kind of compressive load or anything. And,
no, I mean outside of like the mass of the what's happening on the eBay, but it shouldn't really weigh all that much.
Yeah.
What's happening inside the eBay, and I mean those are. If we end up realizing that there is some load that happens on those, like a lot of compressive load, we can replace those easily with some sort of Delrin replacement or something like.
No, I think the way the way it's designed and the fact that both ends are screwed in, are physically attached to the airframe. I think that will alleviate any concern.
Well, and
it's a big deal.
The bolts are sort of sandwiching the plates too. So the plates, they're never like the standoffs are never actually taking any load, or the spacers aren't taking any load. So
Okay. Yeah, I did. At first I was concerned, but once I saw how you had it rigged, but I had it starred on my list. I wanted to make sure I covered it.
Yeah.
So, motor retention. How is the motor retained in the rocket?
So currently, we were originally going to use an Aeropack motor retainer. This is 75 millimeter casing. Is the Aeropack over there? No, it's not. Hold on. Let me grab it real quick. So we have we'll show the motor casing. So we have a 75 millimeter Aeropack. We have the flanged variety. So this is bolted onto. This is bolted onto our boat tail, which is fiberglass. So, and then also what we're gonna do too, this is surprisingly hard to find. This bolt is a 3/8.
Yeah. Don't even get me started. They use the craziest. They get. Well, they use 5/16 on their 54 millimeter, I think, and on 38, which is also really a pain to
Yeah.
find.
So I've looked at the drawings that RCS, the company that makes these, actually shows, and they do not show what this bolt is. So we only
Yeah.
got this in
Yeah.
like last week. This is a 3/8 bolt. So we're gonna put a 3/8 bolt onto the first bulkhead as well, on the lower section. So this will be retained in 2 different sections. For
Okay.
redundancy, and so
Yeah.
why not? It doesn't add
Well,
anything. So.
yeah. And since you had the boat tail, I wasn't sure, but now that I know that you're going to put that air pack on there, that's fine.
Yeah.
And,
Yeah, so that
and honestly, yeah, how's that now? How is the boat tail? Is it like got screws going into it into like a metal ring, or how is the boat tail attached to the?
It's got a coupler shoulder, and it gets epoxied in. So, but it feels a little hard to take
Okay.
off because of the tube running
Boat
in.
tails,
Right now,
yeah,
but
impossible.
basically,
Yeah, you
it
don't.
extends past the fins, and it's all epoxied into this system. We have a little bit of a seam here right now that we need to
Okay.
fill in, but that'll get filled in, so it's a little bit smoother over here and looks a little
Okay.
nicer.
So the aero pack will be bolted to the end of that boat tail.
Yeah, you can see it's
Okay.
actually flanged here. But like you said, just to make sure that we're extra secure, we're also gonna have
Yeah.
the hole is marked but not drilled yet, just because these are a pain to drill.
Sure.
The 3/8 bolt will sit right here. We didn't drill it yet because of also we didn't know what size we
Okay.
needed to drill, and that'll sit here. And so we'll have a bit of a balanced. We'll have 2 different sections. Both of those should be more than enough, but we'll have to.
That sounds good. Yeah, I think you'll be in business there.
Yeah.
Okay, make sure I got that done.
Oh, and I wanted to point this out too, because it's not on here right now. These are just tacked in place right now because we're still sort of in the process of putting these on and making sure they're fully aligned. These have a 1-inch fillet on them. And with a 1-inch fillet, that gives them a do not exceed velocity of around 1900 feet per second. And a rocket never goes more than 900 feet per second. So a little bit over factor of safety of 2 on fin flutter. So, yeah.
That's good though. That'll also protect them on landing.
Yeah.
So that's good. I think you'll be in good shape there. Okay. And no, the fins are just straight G10. Is that correct?
Yeah, you can hear it. They're just solid 1/4-inch G10.
Yeah, we have.
Oh, they're 1/4-inch. Okay. Yeah.
They're oversized, and then sort of right now because we're covering them in blue tape, so we don't have to. We can do a little bit less sanding when we epoxy these in.
Yeah.
But yeah, we sanded down the parts that are actually getting attached right now. We just scuffed them up so we don't have to deal with so they have better attachment to the actual rocket when we epoxy them in.
All right.
So.
And of course, you guys know this, but one thing that always freaks out contestants when they get to the convention center is the safety reviewer is going to grab a hold of either opposite fins or sit side by side and put a lot of force on them to try to bend them.
Yeah.
And just to make sure that they're attached. Those at 1/4-inch G10, they're not going to bend, and you have and so.
Yeah.
I don't think that's a concern, but I think you're in good shape. Just make sure, of course, you stand the body tube well where your fillet is going to be, and the fin as well. You want those areas really sand down to.
And we can actually show.
Get a nice scuffed up.
We do this attachment here too. Like these are basically almost the same system here, and these came out really well. I can take this off the stand. It's a little bit of a pain, but I could stand on it right now and show. Like it's not gonna.
Yeah. No. Yeah. Good. Okay. Just make sure you know. And look at your fins. I can't imagine that's gonna be an issue, but but you'd be surprised at what we see. And then you're just gonna cut the end of the body tube or the motor tube, I assume, off to be flush with the.
This is sort of so we know the length that it goes into here, but it's just like a little easier to handle sometimes, especially once this all gets epoxied.
Sure.
To just have this out here.
And
it's fine. It's just cut, and then this all sort of needs to get just sanded to make sure it's flush, and we'll mount the aero pack after that.
So I guess I don't need to be concerned, but I like the fact that you are going to use a bolt at the top because the aero pack is going to screw into the bottom of that. Of the boat tail, and I got to believe that's just going to be like an epoxy and fiberglass structure, or do you have like an aluminum coupling ring in there, or what's at the very bottom of that?
Aluminum coupling ring. So it's mostly just a fiberglass, and we have a little bit of plywood in there to sort of add some shaping. But
okay,
and that'll get epoxied to this motor mount tube. But again, because the aero pack, we're sort of a little bit, the fiberglass is the thing designed to sort of take the bulk of the force, but because there's a lot of questions about how strong, yeah, we're just going to bolt the top.
Yeah.
So just make the
Yeah, I
question
think that's a good plan, because otherwise I could see, because of course when it hits into the shock cord, that motor, if there's any play at all or whatever, it's going to act like kind of a piston hitting that retainer, and it could. And I've actually seen the air packs where especially if they're like short wood screws into like a coupler, actually kind of shear out of that, or pull out. And one way to avoid that is to not have a lot of slop between the cup, between when you screw that on, so that it's kind of retained it, so that you don't get any kind of play where it can kind of slam into that and try to pop it off. So
I mean, yeah, the Aeropack itself already has a lot of the motor and the Aeropack already have sort of very little play, because Aeropack kind of helps retain the motor a little bit. So the motor should be sort of not moving around all that much with the Aeropack fully installed, but just to make sure that there's really no chance of it moving. Yeah, again, just bolt it.
Yeah. That's good, and I think you'll never regret. That's a good plan.
Yeah.
Okay, well, I will tell you. Batteries. None of the batteries. All the batteries you're using, I saw on the one that using. But you know about the whole LiPo restrictions and all that kind of stuff.
Yeah. So
okay.
The LiPos. So on our payload, we have our COTS battery uses a three 18, or sorry, not COTS, sorry, our SRAD electronics use three 18650 batteries, lithium ion phosphate ones, which are fine in the rules. We have for our payload, a sealed lead acid battery, which is also within the rules of the, so it's a spill-less lead acid battery. So even in the worst, like if you puncture it, it won't spill anything. It is allowed in the DTAG. On the motor, on the DTAG, it states that you're allowed to use sealed lead acid batteries, and also the guidelines released by Ezra on batteries allowed inside of the rocket specify sealed lead acid batteries are allowed. So it's just on our payload. And then aside from that, the only LiPos used are LiPos specified by manufacturers. So the AIM Extra doesn't come with a LiPo, but it does have a manufacturer specified LiPo, and that is allowed in the DTAG. So.
Yep. And I saw that you had the little LiPo that the Featherweight uses for the blue. And that's
so we have the power purge on that. It's worth pointing out on our rocket, all of the switches that we're using. It's not really over here right now, but all of the switches we use are we're going to use magnet switches. That's also part of the reason why we went with this structure for the avionics bay, is it allows us to easily mount switches on the perimeter of the rocket, and all those will be marked. And all of the systems have sort of a way to tell easily from the outside if they're on or off. So we can tell we have our checklist of is the tracker enabled correct? Which flight computers are armed at what time? So that allows us to sort of ensure sort of safety and reliability when we're out there. So yeah.
So you're using magnetic switches to activate the altimeters, is that correct?
Yes.
Okay. So have you used the magnetic switches? I assume that the Featherweight ones.
Yeah. So we have a power perch here that uses a magnetic switch.
Okay. Okay.
And then these will also use magnetic switches. So yeah.
So here's an issue that you need to be aware of. So you've got that magnet on the power perch is on the it's on the end of the power perch, right? And right now it is right next to that that giant steel 3/8 inch structure.
Yeah.
So you have to make sure there's no that's not magnetic.
Yeah.
And so the aluminum might help, but make sure that there's enough distance there. Make sure that you can easily turn off and reliably turn on and off your power perch or any other magnetic switches.
Yeah.
Once where you've got that built. Oh, I see. The one on the right is your test rocket.
Yeah. So this is our test rocket. It's sort of it has a lot of a similar design philosophy, except this one is just a single long one, and sort of to help save space, we decided to stack it this time. Actually, with this rocket, so we can turn on and off with the power perch. The power perch switch is about right there, the magnet switch.
Okay. Yeah.
You just need a really big magnet.
Yeah.
But yeah.
So
yeah.
So
Sorry.
one thing to watch out for then is, and it looks like you have plenty of space, but I use the magnetic switches a lot. And in my 38 millimeter, this is before Adrian changed the design, but I had to be really careful that I didn't they were close enough together because it's such a small rocket that I didn't, inadvertently turn them both on at the same time.
Right.
So I had to be pretty careful, and I don't think that would be an issue, but just as you're kind of laying out your altimeters and stuff, just make sure you get them close to the edge and far enough away from each other that you don't have any issues with the two, with both switches being activated by the same magnet.
And that's something I guess it's worth probably as we lay this out. It's probably what we'll do is we could just lay them out and put them in, sort of lay out some magnet switches on here, throw them into the rocket, and then just test sort of. It's
Exactly.
Probably,
yeah.
This isn't fully laid out yet, but we could change the layout.
And make sure. Yeah. Okay, and make sure that the magnetic switches are not in line with the rail buttons.
Yeah.
Because
we have experience with that.
We learned that firsthand.
Yeah.
I use a tower in for my little 38s and 54s, and I forgot that when I have a tower, I have 3 rail guides I have to worry about, and that actually made it a problem for a couple of the ways I laid out the magnetic switches. So it's not a big deal to have to fix, but you don't want to fix it. You want to know that in advance. So make sure you test that out. Okay, and we are going to provide tents and tables. So there'll be a giant tent and 2 tables. But you'll still want to bring, chairs and other, all the other stuff that you'd want to have out there.
Will power hookups be provided, or?
No.
Okay.
You can have a generator, but it can't be under the tent. It has to be outside of the tent structure.
Well, we don't have a generator. I was just wondering. We have a lot of tools here that are wired, so I don't know. Like if we had hookups provided, we'd probably bring it, but I don't think we're going to bring a generator or anything like that.
Yeah. Honestly, and this is something that you might think about is I have my camper. I have the camper I take, and it has 2 really nice size 12-volt batteries that are also that are recharged by 2 solar panels on the roof. And I just use I have a generator, but a lot of times I will just use a DC inverter to power, and I think the one I have is only good for like 400 watts, so you wouldn't want to run much of anything. But that is something that you might consider would be to bring a deep discharge, like a marine cycle, like a deep discharge 12-volt battery with a little 400, 800 watt power inverter if you need temporary electrical power at your site without having to mess with a generator or anything like that. So that's just something to kind of think about.
Well, I mean, we've never really had to need power at launch
sites. Well, good.
So hopefully we never really should, because like if you're doing something that requires that much work, you probably shouldn't be flying.
That's not a bad, that's a good attitude. Yeah.
We're aiming to have as much, we still have, I believe, a month until the competition. So we have, our focus is
a little bit less than that.
A little bit less than a month now.
A little bit less than that. Yeah. It's a little scary actually.
Yeah. But our plan is to have our rocket pretty much ready to fly well before the competition. So
we're going to be flying it on the 25th at the shootout.
So.
Okay. All right.
Yeah. It won't have everything on board. It won't be like a full Spaceport spec rocket, so to speak, but it'll have enough to really be a quality test flight. So.
All right, good. Okay, I think that's pretty much everything. Looks good. And if you're going to be at the Spaceport Cup, Ken will be there. I'll be there. And so any questions we have, we can keep an eye on it and take a look at it. The last thing it says is make smart choices, be safe, have fun, and do not jeopardize the event. So
actually,
whatever that means.
So one of our sort of our big focuses, you can kind of, I don't know, this is just.
I like this. Yeah.
So we have a big PPE section here right now. It's sort of just like, I don't know, I feel like it's good to show our safety. We have like face shield, safety glasses, work gloves. We bought a ton of, these are just nitrile gloves that we got from someone on Facebook Marketplace, like several thousand of them. We're dealing with a lot of epoxy, so safety. We have a full med kit.
Just in case.
Just in case.
Yeah,
towels, sort of, everything. We have masks, just everything we really need for
A
safety.
stack.
And
Yeah,
then
this
this
is
is just mostly
just
supplies.
extra supplies.
But
That's
just
good.
wanted to show,
And I think in the DTEG it requires who's ever arming the rocket to have, I think, a face shield, if I recall.
Perfect. Well, we got two of them.
we have two of them.
Yeah,
so,
yeah.
this is,
So just make sure you bring all that kind of stuff. And you guys haven't been there before, so you do have to make sure that you're appropriately dressed. It's not only is it hot and sunny like it is in Texas, but to get out to the pad, you have to have long pants and hard-soled shoes, because there's these nasty thorns out there that will go right through a soft-soled shoe really easily, or they'll tear your skin up on your shins. And so, and I've actually had students show up, and I won't let them pass the parking area because those are the rules. And so make sure.
I guess we could take the time to ask, with, for example, charges. How would you prefer they? Obviously, I would assume you would prefer we pack them ahead of time. So we're using black powder charges, just with 4F black powder and igniter shoved into a latex tube. So they're actually fairly safe to handle once they're in that form. But I just want to know, like, I assume you'd prefer we make them ahead of time and transport them, and then.
Well, that's a tough call, and I'm not sure what to tell you. I have to be kind of careful with that one because there's some things. Honestly, so let's say you got stopped by immigration because they stop people along where you guys are. You may get stopped by immigration, asked for, and they'll probably just wave you through. But for whatever reason, if they found what are often referred to as squibs, an E-match or a black powder charge, that might make them kind of nervous. So if you do have them, make sure you have them nicely packed. Or just wait and build them there. But that's, I don't know that I can really give you a one way or the other on that.
It makes sense.
Just exercise a lot of caution with that.
Would you have any suggestions so if we were to say pack the squibs, what would you suggest we transport them in? Like, do you have a specific container that you would say, like, oh, that's a good idea to use? Or we're a little bit inexperienced with transporting them that far.
Yeah. What works well is, of course, you want to twist the ends so the leads are shorted, right? So you should leave them as is, because E-matches almost always have the leads, the end of the leads shorted, right? Kind of twisted together. Make sure you leave them that way. And if you're using, depending how they are, if you put them in a mailing tube, right? So if the charges, so you just put them in a glove, is that right? Or
oh no, we use a piece of latex surgical tubing. It's probably right now, but
okay. So then like a mailing tube that you could slide them into, and wrap them with a little bit of just anything to kind of pad them. Sometimes I'll use bubble wrap or whatever.
We have bubble wrap.
Bubble wrap might not be the best because it's a little staticky, but just anything to prevent them from being jostled around and from breaking open or anything like that. So
and then our motor we're gonna pre-pack ahead of time. With dealing with epoxying the motor grains together, which is better to make sure that we do it all in a safe and not chaotic environment.
So have you built those? Have you built those motors before?
No, I'm gonna go to Ken's next week to go. Some of us are going to go to Ken's next week to work on actually assembling one of those motors for the first time.
Okay.
I understand, for example, like those are epoxied together, and also what's the word? They have a lower grain, and so
that's right.
I've seen sort of enough things to show that it's very easy to mess up.
That's right.
Apparently.
That's right.
So, I've seen all over the place that it happens. So we just really want to make sure that that's not that doesn't happen. And to reduce risk would really just mean just do it ahead of time and make sure that you do it when it's
under Ken's supervision for sure.
Less chaotic and under someone supervision.
So I've been flying with Ken for almost 15 years. We've been going to balls together since about 2010, so a long time. Right. And Ken has flown a lot of big motors, and this is not a knock against Ken, because Ken's my partner in crime when it comes to this rocket stuff. But he has flown mostly all research motors.
Right.
That, in other words, that he's mixed and made himself, and I go out there and I'll help him. So, so before you go to Ken's, you guys definitely read over the instructions yourself, and kind of maybe even do a dry run, so that when you get to Ken's, you are already kind of comfortable with the process. Because Ken's I don't know that he's ever built an M1850 either, and so he certainly has the process down. But there may be very specific instructions for that. So just be careful. Before you get out there, kind of have a good handle on it, so that when you're there, you're not seeing it for the first time. It's
right. I can also reach out to like Harry Spears, for example. I know he probably would also have plenty of good advice. So.
Oh man.
Yeah.
So.
Yeah. Well, good. Yeah, and my concern is that there have been a lot of motor issues with teams building motors without supervision. So obviously Ken will be there, and with Ken there, I have zero concern about you guys.
Okay.
But I want you, but I don't want you to rely too much on Ken. I want you to have your own personal experience, in advance, so that you have a good idea of what you need to do. So that if for some reason Ken couldn't make it, you would still feel fairly comfortable building the motor by yourself. That's what I'm trying to say. I want you guys to have that experience. I believe it should be built under the fly of record. If I was in charge, I'd say, hey, the motor should always be assembled with a fly of record available to help with guidance. And so I'm really glad to hear that you guys are going to Ken's, but still for your own personal edification, I think you ought to read through the instructions and just have an idea of what you got to do. Yeah.
Take your time. Make sure you do it right.
Yeah. And the main reason why is if for some reason Ken can't help you make the motor, you need to find someone else that can, or have enough confidence that you can build it correctly without running into any trouble. So okay. Let me just double check. And there are food trucks that will be out there, but you're going to want to make sure you have plenty of water on your own to drink, and some snacks. Just some high energy snacks that will survive the heat, like not chocolate bars. And good idea to have like a spare change of clothes when you're there, in case you get something spilled on you, or you get hot and sweady.
After Hearn, we've learned our lesson.
Yeah, we went and launched at Hearn a couple of weeks ago, and so we've been
went into the jungle, had to recover that rocket.
Exactly.
It's kind of learning. We got to take the launch PPE a little bit more seriously, maybe.
And all right, and I think we're in good shape. Obviously, you got a little bit of work to do on your rocket, and if you don't get done, obviously you can't fly it. But if you guys are shooting to fly it at the launch this weekend, that's a good incentive to get it done.
It'll be a long week, but we're pretty confident.
It's only a few steps, and like every department just needs to take, like airframe needs a couple more steps, electronics needs a couple more steps, payload. So we'll do that. We'll get that done. It should take a week.
Makes us feel a little confident. This isn't our first rodeo with a rocket like this. I mean, at least this size, it's maybe a little bit our first rodeo, but the rocket's just a bigger version of a rocket we've already built. So for us, it feels not that complicated to achieve everything that we're trying to do. So
great. That's great. And the fact you guys had 2 successful launches, especially with the tender descender, even if you did have slight, some deployment issues, that's a huge bonus. And if you can get another flight under your belt at the shootout, that'll be fantastic. So
sounds good.
All right. I think we're in good shape, guys. Well, thank you. Don't forget to submit this when you're done, and you'll be in business.
All right.
All right.
Thank you so much.
Thank you so much, Tony.
Okay. All right. See you guys at the shootout.
All right.
Really appreciate it. See you next week. Bye-bye.
All right. Bye.